Hello students, now welcome back to the new module of our chapter called as Magnetism. Now students, in this particular module, we'll be focusing on analogy between magnetic field and electric field, which are produced by magnetic dipole as well as electric dipole, right? So let us start with the concept. Let us first revise what is magnetic dipole, right? We know the definition. Let's say we are having a diagram over here which represents magnetic dipole, and the definition is two equal and opposite poles having pole strength plus m and minus m separated by a finite distance to L is called as magnetic dipole, right? So this is nothing but definition of magnetic dipole which we have learned in the first module itself, right? Now next definition that we are supposed to revise is electric dipole, right? As you can see in the diagram, there is an electric dipole which are having two charges minus q and plus q, and these two charges are separated by distance 2L. So if I want to define this particular term, or rather if I want to define electric dipole, so it can be defined as two equal and opposite charges minus q and plus q separated by a finite distance 2L is called as electric dipole, right? Now students, these two definitions are very important. Kindly note it down. Now let's move further. Now we have learned a quantity called as magnetic dipole moment. So if capital M represents magnetic dipole moment of the magnet, then it is given by capital M, it is equal to small m into 2L, right? And this particular quantity is a vector quantity, and it is always directed from south pole to the north pole. That is from pole which is having pole strength minus m to the pole which is having pole strength plus m, right? Now let us move further to electric dipole. So let's say if P is the electric dipole moment which is produced by the electric dipole, then electric dipole moment is given by small q into 2L. And again, this particular quantity is also a vector quantity, and it is always directed from negative charge of a dipole to the positive charge of the dipole, right? So see magnetic dipole, it is small m into 2L, and see electric dipole, it is small q into 2L, and both are vector quantity which are directed from negative pole towards the positive pole, right? Now let us move further. Now let us write an expression for magnetic induction which is produced by the bar magnet at any point on the axis. So let's say I'm having a bar magnet, and let's say we are having point P which is at a distance x, and for a short magnet the formula for magnetic induction is given by B axis is equal to mu naught upon 4 pi 2m upon x cube, right? In the previous module it was at a distance r, so the formula was 2m upon r cube. Right now we have considered distance as x, that's why this particular formula became mu naught upon 4 pi 2m upon x cube. In the similar fashion, the electric field intensity which is produced by this electric dipole at any point P on the axis. So let's say we are having point P and it is at a distance x, and the electric field intensity which is produced by this dipole at a point on the axis is given by E is equal to 1 by 4 pi epsilon naught 2p upon x cube, right? So first one is the formula for magnetic induction, and this one is the formula for electric field intensity, right? Now let us carry these formulas further. Now as you can see, there is a similarity between these two formulas, and from the above discussion we can conclude that the magnetic field which is produced by the bar magnet is analogous to electric field which is produced by the electric dipole, right? So I can say electric field produced by the electric dipole is analogous to magnetic field which is produced by magnetic dipole. In the similar way, I can also say that electric field intensity is analogous to magnetic induction. Now these 2 points are very important, kindly note it down properly, right? Now let us move further. Now let us analyze these two formulas carefully. Now in this particular formula of B, we are having mu naught upon 4 pi, and over here we are having 1 by 4 pi epsilon naught. So if I compare these two formulas, I can say mu naught is analogous to 1 upon epsilon naught. What is mu naught? Mu naught is permeability of free space. And what is epsilon naught? Epsilon naught is permittivity of free space. At the same time, I can say magnetic dipole moment is analogous to electric dipole moment, right? Now this analogy is also very important, because using this analogy we can write formula for electric dipole using formula of magnetic dipole. Now let us take an example. Now let's say we are having a magnetic field and a bar magnet is placed in it, and we know formula for torque. What is formula for torque? Tau is equal to vector m cross vector b. Now we know that vector m is analogous to vector p, right? So let's say we are having a dipole, electric dipole, which is placed in the field, and it will also experience a torque, right? So let us write the expression of torque using analogy. Now we know that vector m is analogous to vector p, right? And at the same time vector b is analogous to what? Vector e. So therefore formula for electric dipole will become tau is equal to vector p cross vector e. So this is how, by using analogy, we can convert the formulas of magnetic dipole to the formulas of electric dipole. So the only thing that we need to remember is vector b is analogous to vector e, mu naught is analogous to 1 upon epsilon naught, and vector p is analogous to vector m, right? So in this particular module we have learned analogy between electric and magnetic field produced by the magnetic dipole and electric dipole. I'll see you in the next module. Till then, keep learning.